Hi AP Calculus students. Today we are starting a whole new unit. We're moving on from limits. Still need to know about limits, but we're moving on to another unit where we're going to be focusing on instantaneous rate of change. So our learning objective for today's lesson is how do we define an average rate of change over an interval, and how do we define an instantaneous rate of change at a specific input value. So I want to start off with a warm-up that challenges you to think about what is average rate of change and what is instantaneous rate of change. So let's say that I'm going to Northern California for a vacation, and I leave my house at noon and travel for almost 8 hours. So this is a graph of what my journey could look like. It's not the most realistic, but this is what it could look like. And so I start at noon, which is 0, and travel for almost 8 hours. So you can see I stop. We're gonna say it stops a little bit before 8. And here is over time how far I have driven. And so I'm gonna challenge you to think about what is my average speed between 2 and 5 p.m. So you can see the points between 2 and 5. So what is my average speed there? I'm going to give you a hint and remind you that speed you find using miles per hour. Okay? So I'm challenging you to think about how would you find the average speed between 2 and 5 p.m. and then how would you best estimate your speed at exactly 2 p.m. Here's my answer. So what I did is, since speed is in miles per hour, I found the change in y over the change in x. I found the slope of this line right here. I found the slope of this line that connects those two. Okay? So that line, the slope of it, the change in y over change in x, I estimated the distance at 5 p.m. to be about 350. So this is an estimation. I estimated the distance traveled at 5 p.m. to be 350. And then the distance traveled at 2 p.m. to be 70 miles. And then I did change in y over change in x to get 280 miles over the course of the 3 hours. And then dividing that, I got 93.3 repeating miles per hour. So I was driving very fast. Good thing I didn't get pulled over. So that's my estimation. I hope you got something similar to that. The exact speed at 2 p.m. is a little trickier, and at this point we don't really have a good method for figuring that out, so that kind of was a guess for you. So the hard part about this is we're only given one point, so we're trying to figure out, okay, exactly at this point, how fast was I going? And so we need to find now the slope of this line, but finding the slope of a line with only one point is very challenging. Okay, but we're going to figure out how to do that today. I just gave a guess of about 60 miles per hour because I know that that slope is less than. So my slope before was 93.3, and then the slope got less steep. So I estimated about 60 miles per hour. But you could have gotten a different answer. Okay, let's look at some definitions of these lines that I've been highlighting. So the average rate of change, I'll highlight in blue. The average rate of change is the slope of the secant line over an interval. So there's my secant line. Okay? And so the secant line over an interval basically means like over a period of time. So you need 2 points. This is over a period of time. You need 2 points. So you see in the graph I have 2 endpoints, and the secant line is the slope that connects those 2 points. And so average rate of change is the slope of whatever that secant line is. And then instantaneous rate of change is the slope of the tangent line at a point. So this is a new vocabulary word, tangent line. And then instantaneous rate of change is the slope of that tangent line. So this is called instantaneous rate of change because it's happening at a single time. So it's change at a single moment in time. Okay. So secant line and tangent line. At this point, we're going to derive the equations for each of these. So you should have a pretty good idea about what the average rate of change is. We're going to derive these formulas given 2 points. So I'm going to mark the point A and A plus H. Now I'm going to say we need to find the average rate of change between A and A plus H. And so that means we are finding the slope of this line. We're finding the slope of this line. So I'm going to highlight that again in blue. So my average rate of change is this blue line right there. Okay. So in order to find slope, I do need to know my rise over run, my change in y's over my change in x. Okay, so in this case, I'm not given specific x values or specific y values. So for my y values, I'm just going to call the y value here f of a. That's my output. And then the output for the other point would be f of a plus h. So the average rate of change will be my change in y's, so subtracting these y values, over the change in x. Okay. This is very formal notation, but this is the way that calculus defines it. So really, it is just change in y over change in x, but in this case, our y value is f of a plus h and f of a. And this is what we call, another vocabulary word here is difference quotient. So difference just means subtraction, and quotient means division. So it's a quotient that shows the difference between those 2 points. And now is the hard part. So we kind of already should have had a good idea of what average rate of change is, but our real lesson today is figuring out what is instantaneous rate of change. So I'm going to go to a little Desmos graph to highlight that. So here we go. Here's a Desmos graph where I can calculate, this m here is calculating the average rate of change. So it's finding the slope of that line. And you can see that it has my difference quotient right there. So my h value, I'm changing the h value, and the starting point is at 2. So it's saying let a be 2, a is 2, because that's where I'm starting, and then I'm changing the value of h, and it's calculating my average rate of change using that equation we just wrote down. So if you need to pause for a second to compare the two equations, go ahead and pause. But we want to now think about what is the instantaneous rate of change. So we want to think, what is the instantaneous rate of change when I get close to A? So at A. So in this case, that means at 2. So I am going to start moving my h value to get closer and closer to 2. So I can find the instantaneous rate of change. The instantaneous rate of change at 2. So I'm getting closer. Okay, I'm at 3. I'm going to zoom in. I'm going to zoom in this way. Okay. So I'm getting closer. Getting closer. Ooh, I'm very close. So I'm at 2.25. And the slope is looks like it's getting closer to 5. Oh no, but it just got lower than that. So I'm getting closer. Getting closer. Very close to 2 at this point. It looks like the slope is getting close to 4? Oh no, what happened? When I got so close to 2, my h is now 0, and my slope is undefined. my slope is undefined. And that's because if I have these 2 points and I did change in y over change in x, I get 0 over 0, which is my indeterminate form, 0 over 0. Shoot. So how are we able to figure out if I can't get on the point, but I can get close to the point? Can't get on the point, but I can get close to it. What is that calculus topic that we just learned about? Limits. Oh, we have to find the limit. So we can't look at the function value. We have to look at the limit as we get really, really close to 2. Obviously. Okay, so that is what our instantaneous rate of change is going to be. If I want to find the rate of change right at point A, I have to find my average rate of change. So it's going to be the same thing. And I hope you can see a plus h minus a is just h. So we can just do that little shortcut. That's just h. I hope you can see that now. And then we're going to take the limit as h gets closer to 0. So this value h is going to 0, so that those 2 points are getting closer and closer and closer to each other. So we need to use limits to find the instantaneous rate of change at a single point. This is an equation you have to memorize, but you can do it. I believe in you. There is one alternative equation. If you think this equation is too much, there's another form that you can use. Here is the other form. It's very similar, but sometimes students think it's easier. We could look between a and x. So basically, instead of a plus h, if the a plus h concept is weird to you, then you can just think, okay, finding the average rate of change between a and x. So I'd have f of a and f of x here. And then my average rate of change would now be between a and x, and that would be f of x minus f of a over x minus a. This is my new difference quotient. And so, to find the instantaneous rate of change at the point x equals a, I would use my difference quotient, so using my same average rate of change. But now I'm thinking about the limit as a and x get closer together. So the limit as x approaches a. So either of these definitions work. Both limit definitions of the derivative, you can decide which one you like better. Let's do some examples. So these first 2 examples are of average rate of change. So both of these are hypotheticals of people driving helicopters, okay? On the left, I have the altitude of the helicopter given by function k in a table. And then on the right, I have the altitude of a helicopter given by function e in equation. Okay, so you can pause for a second to write these down, and then we'll go over them. So first, let's look at the problem part A. Part A asks, what is the average rate of change of Kong's helicopter altitude over the interval 5 to 20? So the time interval between 0 minutes and 20 minutes. 0 minutes and 20 minutes. Indicate unit of measure. So this is always important. We always want to include our units, similar to how I did in the warm-up, miles per hour. It's just very essential on the AP exam, so don't forget your units, y'all. So I'm going to be using my equation. The average rate of change is k of 20 minus k of 5 over 20 minus 5. So change in y over change in x. Just using that basic average rate of change equation. So using my table, k of 20 is this point. So that is 15,000 minus k of 5 is this point. So the output is 3,500 over 20 minus 5, which is 15. my units are feet per minute. And honestly, I could leave it like this. So if this were the free response section of the exam, I would just leave it like this, because once you have your equation set up, that's as far as you need to go. The AP exam free response section does not make you simplify. Oh my gosh, what a dream. I don't have to simplify. The only time where you will is if you're on the multiple choice section. So if this were a multiple choice question, yes, you would have to keep going to figure out the right answer, do a little bit of simplification, which is 2,300 over 3 feet per minute. So if this were multiple choice, you would maybe have to go that far. However, I think you can get used to leaving it in answers like this, because sometimes we make mistakes in the simplification, and you wouldn't want to get it right up there and then make a small algebraic mistake and get it wrong and then get the whole problem wrong. Okay, so that's just something to kind of think about. All right, and now the problem on the right. I'll switch colors. Now we have an equation. What is the average rate of change of Estelle's helicopter's altitude over the interval from t equals 5 to t equals 20 seconds? Indicate units of measure. So again, now using e of 20 minus e of 5 over 20 minus 5. Now I do have to plug into the equation, so I'll do it down here. That will be negative 11 times 20 squared plus 920. And I'll put it in parentheses. Then minus e of 5. E of 5 is negative 11 5 squared plus, oh gosh, I ran out of space. I gotta super zoom in. Plus 900 times 5. And I definitely want this one in parentheses because it's being subtracted. Okay. And then all over 20 minus 5, which is 15. So I actually could leave it like this. I could leave it like this. I would want to add my units. So this is feet per minute. Again, so I would just add feet per minute and then I'm done. If this were a free response question, I would totally just leave it like that and not do any more work. Because who needs more work? Not me. If this were multiple choice, we would have to simplify to figure out the correct answer, and you would end up with 9,375 over 15 feet per minute. Okay, so if we had to do a multiple choice, we would do that. So I would definitely remember, don't simplify if you don't have to. Okay, now let's do an example of instantaneous rate of change. We got to use that big bad equation. So we're using Estelle's equation again. So same equation as the last problem, so you don't you don't necessarily have to write this again because it's the same. But part C says, write an expression involving a limit for the instantaneous rate of change of Estelle's helicopter altitude right at time t equals 7. Okay. So I want you to kind of try to write down the instantaneous rate of change, the slope of the tangent line, before I do. So use that definition to try to remember what it is. Okay, so we have two forms. We have, I'll do both. The limit as h approaches 0 of f of a plus h minus f of a over h. And then we also have the alternative version, which is the limit as x approaches a of f of x minus f of a over x minus a. So for now, let you do both as well. Let's have you practice both, and then you can decide which one you like. So in this case, my a value is 7, because that's the time that I'm looking at. So what this is looking at is a equals 7. So that's the time at which I want to find my instantaneous rate of change. So that is what I'm going to plug into the equation. And I'm just going to plug it in right here. So I'm going to replace all my A's with 7. I'm just doing a little shortcut. There we go. Cool. Shortcut complete. So I'm looking to find the instantaneous rate of change at 7. So let's focus on that top equation first. So f of 7 plus h means I'm using this equation. So that will be negative 11 of 7 plus h squared plus 900 times 7 plus h. Whew. And then I'm subtracting f of 7. So f of 7 just means I plug in 7 into the equation. Like that. All over h. Oh my gosh, I forgot the most important thing. As I'm doing this, can you think for a second, what is the most important thing that I forgot? Oh my gosh. Moving this over a little bit. Forgot my limit. Okay, so this is the limit as h approaches 0. I need that because I can't just plug in 0 because look, I'd get an indeterminate form. But we all know how to deal with indeterminate forms. We're not going to simplify this right now because it just told me to write an expression, and I'm not going to do more than I'm asked. So I wrote an expression involving a limit for the instantaneous rate of change. I'm not going to simplify this. We are going to have ones where you'll simplify in the future, so savor this moment where I'm not making you simplify this and say, thank you, Miss Patterson. Oh, so nice. Okay, so that is one expression. Now let's do the other one. This time I'll be very careful to add my limit as x approaches 7. F of x is just my equation. I'm actually going to change these to t since it technically is using t. My function is using t. So instead of x, I'm going to write t, just to be true to the original equation. So f of t is negative 11t squared plus 900t. And then I'm subtracting f of 7, so very similar to what I did in the upper equation. All over t minus 7. All over t minus 7. Again, I could simplify this. You could simplify it too. But I'm not going to because it didn't tell me to. Okay. Alright, we're going to end it there. So hopefully you feel better about finding the average rate of change, what the average rate of change represents, and then using our limit equation to find the instantaneous rate of change at a point.